All right, continuing with our project, we see that all our tests are still passing with the simple struct, and then these not so simple ones, and these ones. One thing we're not testing is multiple structs, right? So only outputting one here. What if we have multiple structs in the file? So like this, func test multiple simple structs, and that's the simple struct there, and then there's the also simple struct, which is world, and we would expect also a simple struct to be object there, and we get that the test fails now. Yeah. Just multiple structs, just output part. Wait, is that it? That's what it's outputting? Nah, surely not. I'm a bit confused, right? Because I feel like we don't support this. But I guess we do. Where? It's going. Yeah. Yeah. Or is it the new line? He's I don't even know it's different here. Not super sure. But how about that? So I guess our code is, I guess we wrote the code in a bit of a smarter way than I thought. So we append object for struct list. Yeah, interesting. Yeah, we're definitely doing that. So we do the input line variable out. That's the input line there. Yep. New line there. Is it need of an extra new line? So like this. Don't really know it's different. Is there a way to do test text diff? Golang testing text diff. Testing method, is there a way to show diff? No, you cannot do this. Yeah, I mean, it's definitely there, right? Also simple struct equals, I mean, let's copy this here. Let's put it there. Nope. Nope. Yeah, it's kind of weird, but don't really see what's wrong. T.log length of output parse, T.log valid, what's validator, length of that. And 55. So, oh, I'm space being thick. This is world. There you go. So we do have multiple structs working. That's great. Testing multiple structs. Okay, the next case that I want to support is if you have type my struct, and in here you have embedded structs, so nested type other struct hello string, right? You have that. In here you have hello. Oh, sorry, other struct. This is then going to be the other validator. So where is it? Testing validbot. Yeah. If I have that and I have, let's zoom in a bit here. That's fine. I think this is okay. Const other struct parser, which is object that has world. And can I do struct parser here? Yeah. Nice. Yeah, that's cool. Const x is other struct type. Other type of? Is it? No. Oh, it's infa type of. Oh, I don't really know actually. What is it? Invalid bot. Others dot. Bra dot infa dot type. What is it? I'm gonna have valid bot. Intro output. They called it type output. Output type of that. Yeah. World, which is not below. Right. Yep. Great. So we want this basically. Test nested struct. So we have this. What I'm going to expect is this, and I'm going to expect other struct to be an object hello string, and I'm going to expect my struct to be an object of nested, and this is going to be other struct, comma. This is going to fail now. Because it sees. Oh, what's it doing actually? Line 150? Well, this is failing now. Why are you failing? You're not failing. That's weird. Seems like this was failing almost randomly. Cannot find corresponding JS type. Yeah, that's correct. Because get JS type. What if? Oh, what are you doing? Oh, that's weird. Parse like that as well. Get JS type. Do that print line. Type. Actually. Oh yeah, this is not quite the function, is it? I want struct est to list is here. Type identify to the print line field. Do that print line field type. All right, and it says other struct here. Great. And it says other struct. What we have to do is we have to Can I in Go have type string struct? No, I cannot. So one less problem. The type from get.js types is going to have to be a little bit more complicated. And one of the things we're going to have to do is a double parse, because what you can do is... Oh wait, do you? No. No, you don't, because you do them all. So I thought we would have to do a double parse at some point, but I don't think we do. Reason being is that we put an array of name type. Oh, but this is struct st list, which is called the parse struct fields goes into a struct list, which is really a map, and goes from there. Yeah, and we take that map. Struct list is a map. Yeah, good. And structs to valibot. We're going to have to do the ones that don't need nesting and go from there. But oh, I can think of one strange edge case here. Well, you can have circular relations that kind of go on forever, but that's a bit silly anyways. Okay, we take the struct list, we construct these, and we say get.js type. And the thing is, if there isn't a JS type, then this struct isn't quite ready. Maybe, oh, what we can do is we can check the type. Aha, so if error is not equal to null, actually let's do a list of errors up here. var or const no JS type, which is errors.new cannot find corresponding JS type. Where is this? Ah, okay. No JS type. And the reason I want to do that is just to be a little bit more firm here. So if I say, what I'm going to do, I'm just going to say if error is equal to no JS type, which for now is the only one that that function can return. That might not be in the future. I can remove that for now though. Keep it simple. So if error is equal to that, equal to that. Here we must have a nested struct. Okay. So now what we're going to do is we're going to say we are going to say what are we going to say? We're going to say, oh yeah, because actually we can't quite, now we don't want to, we want this bit of code to run on the else. It's not very clean, but if it is a struct type, we don't want to append it to a list of the validators because we don't want to add it to our import line. But basically here, we're going to say that JS type is equal to field type dot type. Curious to see what this returns. Okay. Oh, okay. So, okay, yeah. Let's put these 2 lines on something else here. And get rid of you, get rid of you. Okay. Well, here what I'm going to say is I'm going to continue so we can, you know, not have remove 1 layer of indentation and do remove those there. Not JS type, but fields type.type. Great, that worked. Feet nested structs working. All right, that's cool. Can we think of okay, let's push this a little bit more. Test multiple nested structs. We're gonna have A have a field A, it's gonna be string, B which is gonna be type C, and D which is gonna be type E. We're gonna have type C, B struct, C has hello string and also has A which is also E. And then we'll have to define E, which is a struct that has, let's say world, and let's make you floats. Boolean float 64. So we're going to need object string Boolean number up here. We're going to have A, which is equal to object. It's going to have A inside, it's going to be string. It's going to have B, which is going to be C. It's going to have D, which is going to be E. We're going to have C, which is object that has hello, and that's string. And then A, which is E. Const E equals object world Boolean 1, 2, 3, 4 number. Actually, Validators does have validators for just ints, so I think I will consider that pretty soon. Alright, what happens here? Boolean, oh, because I wrote Boolean, not bool. Now it does import Boolean, and it does so before it imports number, because yes, it should do that stuff. Okay, and actually that looks correct. Object string. Ah, wait, what the hell? Object. Wait, is that? Oh, okay, that's not right. That's being, oh, we're having the same issue that because it was a map, right? The structs are being printed out in a weird way. So we can't quite have a map. We need an array of structs. Yeah. Type struct, which is going to be a name, which is string, and then fields, which is an array of name type. Struct list is an array of struct. And here, struct underscore SSAS. This is going to be s dot name, and a range of s dot fields. What's our other error? Make struct list 0. Struct list is equal to append struct. It's gonna have a name. struct name, and fields, which is going to be struct fields. Great. Hopefully everything still works. Okay, and it is no longer do we have a map that gives me some random stuff. Alright, so object string boolean number, object string boolean number, correct. Const A strings, B goes to C, D goes to E, perfect. Const C goes to object, hello is a string, A is E, and const E equals object world, and then the correct number of O's, I hope. 2, 3, 4, 1, 2, 3, 4, number. Okay. What's wrong? God, these are always so hard to spot because I just don't really know what's wrong. There's a new line, yeah, that's correct. I also have a new line there. I have a new line right at the beginning. I'm not sure. A, C, E, world, boolean, string, string. Object string boolean number. Yeah, I mean, I'm comparing this to this, and it looks just completely identical. Let's check the lengths. There's an extra character somewhere. Oh, semicolon. Who knew? Okay, good. It's working. I think it's working well as well. I think, do we have to deal with anything like this? Some stuff not being typed first? Like, yeah, C is used before it was assigned. So yeah, this is slightly annoying. Block script C is used for assign. If these were all vars, I think this would fix itself. Right? Be like var. I know it wouldn't. But this is a TypeScript, actually, yeah, TypeScript complaining, yeah. So what you have to do is you have to do a topological sort. Ooh, fun. You have to do a topological sort. Really? I can't believe TypeScript doesn't handle this. Why do I have to handle this? Come on. I guess because their value's not types. Used before being assigned. TypeScript used before being assigned. Do I even need this? Like, because obviously there. Yeah, I guess there's no easy way around this, to be fair. You have to sort. Topologically sort, you have to go through A and its dependencies and create a graph. So we say that A, so let's grab GIMP again. Yeah, this. Let's get a new one. Let's there we go, shift bucket, not bricks. Defaults to bricks. All right. Let's back to the drawing board with this. With what I mean by topological sort and stuff. Let's grab a pencil and let's do this. Yeah. This. All right. So, if you have, like in our code, we have A depends. A depends on. Well, this is still like really big. Let's go down even a little bit more. No, no, what are you doing? I swear I don't understand this. Where is my pencil gone? What? Genuinely, where's my add tab device? Bro, what? Two options. Oh, there you go. Okay, we're going to a 5. There we go. Nice. So we have A that depends on B and E. No, depends on C and E. And then we have E doesn't depend on anything, but C depends on E. So, first of all, you have to build these relationships. Right, you have to build all the nodes in the graph. You have to build this, and you have to topologically sort. Do you, or do we just go from the end? Like we go to nodes, because remember C could depend on something else as well. Let's say F. The algorithm for this is like so clear, but we walk the graph, walk until node with no neighbors. What this will never allow for is A depends on B depends on A, which we might want to allow, maybe, but not now. Before we do this, because this is not really a problem most of the time, Typescript use const before being assigned. So we'll do that. Should this have thrown a variable of its own? Do wonder if there's a way for us to solve this. Such that all of these have access to each other. Like if I was to run, oh, wait, can I just ignore that? Variable is used before being assigned. Used before being assigned TypeScript. Just I guess what we could do is E because that's 2, right? With the exclamation mark, you get one. Block scoped variable E. Scoped variable used before declaration. I don't think this is very much. This doesn't really do much for us. This also doesn't do much for us. No use before declare. Do you, like, would this build TSC, if I run TSC? Yeah, so who's crying at me? Structure. Because if I went and said console.log a.safe a.parse. Wait, what is this? Okay, a parse a type pipe. Oh, it's safe parse of a, and the input is something like not bruh. Ah. Wait, what? Cannot access uninitiated variables. Well, like string. Or is it actually that this would have this has to go up there? And you have to be here. Yeah. I mean, yeah, then the correct way would have to be walking a graph and stuff. But what if I did let A, B, and C, and then I did this, and you are... no, but this would break quite a few of the types, right? Yeah, okay. So we do actually have to. There is a reason for us to do this. And would this be? TSC ignore errors or something? I don't know. TSC help grep errors. Error. Nope. Typescript compile on error. Compile code with errors. No emit on error true. No emit. Okay, still complaining. So, okay, well, it's a fun problem to solve anyways. But yeah, what about stuff like this? You'll never have const f, which is object of hello e, and then here this would be world f. You're never gonna have this. But how useful is this anyways? Could you do e? No, not really. Okay, limitations. No worries. Let's assume no cycles. Then we can walk until we find this and this. We tick those and then we walk until we find. So it's a DFS, right? Yeah, it's just a DFS. Pretty interesting problem, actually. Didn't think I would have to deal with it, but I do, so it's nice. Right. Let's get working. Let's put the drawing tablet away. Okay. Back to the code. After I get all the structs, I'm gonna have to know which one to put first. Right, I want to know I need to know the list of, I need to know their dependencies. So I'm going to create some more types. I'm going to create type the node, which is a struct. I guess we can give it a name, like that's going to be the name of the struct. And then we're going to have the edges, which is just going to be more nodes, an array of nodes. Yeah, and it's going to have visited, which is a boolean. If I do that, okay, nice formatting. Visited is a boolean, it's going to start off false. And then we're going to go and say, going to modify these nodes here. I think do we do pointers? We can, but we don't have to. Maybe we should. Yeah, I'll leave it. Because we're gonna, so we said assume no cycles, so there's no need. But I did interestingly see a very small video, very good video on YouTube that said that pointers are faster than embedding the struct like this, because this is going to create a struct with an array inside, so it's going to be quite a bit of contiguous memory. I don't really know that makes it slower, but I think it generates more garbage. From what the video said, it was a lot of garbage collection, performance loss. But anyways, okay. So we're not going to change this function, structs to value, but although we kind of maybe should. This struct list. Oh no, we can actually change the order of struct list. Okay. So we're going to take struct list. We're going to change its order. So we're going to make a function. Struct. Is it func order topologically just order struct list, which is struct list returns a struct list, and we're just going to mutate. We're going to mutate it, or we can create a new one, it doesn't really matter. Now what we're going to have is we're going to have to start by making the nodes. Make the nodes and make neighbors. Okay. Right. So for s in the range of struct list, s dot fields, yeah. So node, which is node, name, s dot name, and then it's going to have nodes, edges even. It's going to be a make of that, yeah. For fields in the range of s dot fields, node dot edges equals append fields dot type. Okay, actually we're going to do if not error get just type fields dot type if error is equal to if error is equal to nil, or error is not equal to Node.js type, we continue. Otherwise we do edges append oh wait, we have to construct them all first and then go through their fields, because we're going to have a map. Yeah, we're gonna have a map node map. so in original. I hate it. Make of a map, which is struct name and a node, and this is actually gonna come after. I'll sort that out in a second. And we're gonna do node map at node.name equals node, and in here we go for each one struct name node in the range of node map. We go for underscore field of in the range of node dots oh right, yeah, because here I kind of lose access to those. Yeah, otherwise here I'm going to lose access, so I'm going to make like an intermediate. This is kind of ugly, but node with index to the original. Yeah, ugly, I'll rethink it, but index is going to be int, and the node is going to be a node, and it's going to be node with index. Node with index. It's going to be node index I. This it's not very pretty, but what it will let me do, node, let's say node, in the range of node dot struct list at node index dot fields. There we go. And then here we go field dot type, and then we can go node dot edges equal append node dot edges field name, and we don't need you anymore. Field name append. Oh yeah, it's gonna be node map of not. Whoa, wait, hold on, what am I doing? Here we have a node, and if it is error is null, it's not Node.js type error, so we only want Node.js type. Actually, we don't need that equals nil, just that. We want to append onto those edges node dot node oh, there's duplication errors that are gonna come up. We want to append a node, and the node is gonna be node map at field dot name dot node. That's it, perfect. And this will definitely need testing of its own, but we should now have at least something. Right, yeah, we constructed the graph. And it's a lot of coding without testing, but now we have to walk it, I guess. Yeah. And the output I want is to have the graph be the other way round. No. I want topological order, so the output of this could be F, E, has to be C, and A always comes last. It could also be E, F, C, or A. These are fine. So basically like a list of these. Okay. So gives you a struct list. Yeah, it's going to give me a list. We can definitely make this a bit more generic, so that'll be much easier to test as well. Right. My god, I keep on blanking. So I have to do a depth first search until I have reached all the nodes. So I'm going to say func dfs, that takes in a node, and it's going to return, in this case, just string, I think. Because what's going to happen is, okay, depth first search, what happens is we do a loop. Right, there's a way of doing this non-recursively as well, of course there is, and it would be easy, but if you're going to do it the recursive way, where we take the edges, we go for the first non-visited, right? We go for, for underscore node dot n in the range of node. And right, node dot edges. Nice. Okay. If n dot visited, and we continue. And we go, well, otherwise we do DFS on n. When we get through the for loop unaffected, that's when we hit our base case. And our base case will be to return node.name. I think that's right, hopefully. Oh, and before we return that, we do node.visited is true. Return, let's just say nil for now. Let's actually do another file called topological.go, topological._test.go. Whoa, that's not go. And here is where we're gonna have the code. It's gonna be package main still. And we're going to have this be declared here instead. This kind of intermediate function we will test, but not quite yet. Okay, so this is pretty simple to a logical order, where when we need this other function of logical order, where we take in node, and what we return is string. So let's imagine we are a node. We go DFS, we return name. Oh, and then okay. Yeah. Order. Wait. Hold on. Yeah. I guess we can. Do we return? Yeah, actually, it's going to return an array of string, I think. And what it's going to do is it's going to take one in as well. Or is it? Doesn't have to take one of them in. But it returns one. And at the top we can declare one each time. Oh, this is going to be very memory heavy. Yeah, super memory heavy, and we don't need it to be, but it's optimized later. Ordering, which is make string 0, ordering equals append string array. Yep. And then here we go, ordering append node.name. We append after, we return ordering. Great. And here, did I have anything? No. Func test basic order. Let's test single and t testing.t node, which is a node. It's going to be visited. False edges make this 0. Ordering. Oh, it's gonna have a name too. Name, say A. The ordering, which is gonna be a string array with just A inside, and we go slices.compare. Compares the elements of using compare on each pair of elements. The elements compare sequentially, starting at 0 until 1 and it's not equal. The result of the comparing the first non-matching elements return. If both slices are equal until one of them ends short slice. So the result is 0 if. Oh, okay. Okay, so we want that to be equal to 0. Correct order test order, which is DFS of node. Compare correct order and test order. And we're going to t.log test order. Test order if it's not equal to 0. T.fail now. T.log structs slices are not equal. Alright. Wait. Hello? Can I get some? Oh, is it that it just actually is? That they actually are equal? Yeah, fair. Okay, so let's say n1 n2. Let's make simple. Right, n1 depends on n2. Edges append n2. Let's go from n1. Oh, something that is a bit funny is that this isn't. Oh, sorry. It's that we need to find the root node, right? And I don't. You have no guarantee over what the root node is. A, B. So the correct ordering here would be A. No. B has to be declared first as independent anything. A comes after. Yeah, that's correct. But the thing is, I have to feed it n2 because if I feed it n1, so if I feed it n2, there's no edges to go on. And there's no edges to go on, so you know what happened. Yeah, I swear, I've done this exact problem at uni actually. It's actually algorithms coming in handy. But it's now skipping. I'm missing it. So I guess we go through. I guess we iterate through a slice of all the nodes, and what? Yeah, because we definitely have to go through all of them. We just take the longest ordering. That sounds stupid, but I think it would work. Can I do spread? No. New ordering, which is DFSN. Oh, actually, I can do slices dot concatenate. Concat returns a new slice concatenating the past in slices. Because it's going to be slices. Slices. My slices, which is going to be an array of string, which is going to be ordering and DFS of m.n. My slices here. Or is this ordering and DFS? And yeah, that makes more sense. Still running? Yeah. Great. And here we're gonna run func topological sort, which is actually going to take nodes, which is an array of node, return string. So longest string? I don't know, man. This seems longest. Which is equal to an array of string n of nodes in range of nodes if DFS. Okay, I'm gonna do order is DFS n if the length of the order is bigger than the length of the longest, then longest is equal to order. Can I do that? Yeah, I can. Return longest. It looks very silly, but you know, looks silly and it works, maybe not so silly. Node slice, which is a array of nodes, and it's gonna have a node in there. Node slice. There you go. Yeah. It's gonna have n1 and 2. And one thing I do want to do here as well is do it the other way around. So I want to, oh yeah, it actually shouldn't matter here, but just to be really safe, right? Do it the other way around. Okay, good. That really hacky thing here works, but horrible. Feet, but not very nice. Logical sort algorithm works, but is not at all efficient. But we'll come back. Maybe. Topological ordering functions. Okay. Now let's do a more complicated test. Test complex. So we're gonna have n1. That is A. We're gonna have n2, which is B. N3, which is C. Let's do n4, which is D. 5, which is F. So let's say that n1 connects to edges n2 and n3. Let's say that n2 dot edges connect to edges dot pen. So n2 connects to n4 and n5. n3 dot edges connects to n5. And n4 dot edges connects to n5 too. So yeah, I think that's okay. And then the order here. So basically all of them depend on this. So it's always going to be F first, and after F it should be N3. Right? Go on N5, yeah, F, and then N4 is D. And there's 3, actually it could be D or the N3, which is C. D or C, it doesn't actually matter that much, but then it's B and then it's A. Let's kind of randomize it, I guess, a bit. 5 and 2. Oh, down here. Yeah, we don't actually want this test anymore. Okay, so that's not equal because the test order returns 3 BCA. That's pretty weird. Alright, let's simplify this a bit. let's say that n1 depends on n2 and n3, and that n2 depends on n3. So everyone depends on n3. C, and then it goes to B, and it goes to A. Do you work? You don't work. Why are you saying B first? B definitely isn't first. You're going B, but N2 depends on C, so that's wrong. Is it one of these weird things where I'm returning the longest is a bit funky? Okay. Say we get the node correct up there. Go for string. Go through the edges. Then we concatenate the search for the next one. Oh, but what's the order? Actually, I have concat. Should be correct. Should be correct. All right, debugging needed then. fm2.println ordering, and I also want to print n.name. So we have B, and we concat B. Wait, what? Excuse me, what? That's weird. Okay, let's think then. Go, and actually let's make this even easier. Let's say test order is equal to DFS and just give it the root node. It still gets it wrong. Okay, that's fine then. So it's not a weird, dodgy, longest thing. Because we give it n1. N1 edges equal to this. At 23. So it goes into here, or actually goes into the FS, makes a string array. If it's visited, we continue. We say that the orders, this is like the concatenation of DFS of B. So B, just N2 actually depends on C. So let's say from t.println node plus node.name. So it should go, oh god, ABC. Oh, right, let's do t.skip for both of these. And then just have that last one. Node A, B. Yeah, node A. And then the next one to come along is going to be node B. And wait. The ordering for B is itself, which sounds weird. So we go, A comes in, it looks for its edges, it finds B. It's not visited, we continue, we go DFS and B, it goes through its edges. Node plus edges, node dot edges. do the print line edge not name A edge B. Let's do another print line of something. There goes node B, just there, and then goes there. I don't seem to print like edge. Does B not have the edges? Edge length of node dot edges. String of that, I guess. No, can't do that. Print F. Is it X? I can't remember V. There you go. B has it. What? What are we doing? We're appending on 3. Oh, is this a... Because they need to be pointers then. Yeah, they definitely need to be pointers. I see what's up, because it's embedding the different edges on every single one. So, okay. Yeah, I understand now. Node star. Do you have to be that? There you go. It's the only change we have to make there. There's a few that we have to make up here though. The pointer to that, this, the Go LSP is so fast, it's unbelievable. This, right. Oh, wait. Oh, here, here. Cannot use node index. Node index, you have to be that. No. Is this node map field node pointer? I cannot use node edges. Append the node. Append the pointer of the node. Append the star? What are you talking about? The pointer of it, yeah. Cannot take address operator. Address operand, yeah. Kind of confused on that. Node map. Oh, I guess node map can be node with index, and this could be pointers to nodes as well instead. Take the address there, and yeah, that should sort itself out. Okay, now we have some more real results. So we go A, the length is 2, then we go edge B, the edge length is C, we go to C node C, doesn't do anything. Then we print the order C. We get C out, and B gives me C, then B, we get to edge C from A. Yeah, slices dot do remove. I basically want to remove duplicates. Golang slices remove duplicates. There's yeah, I'm gonna be a bit lazy right now. Just I have this, and this is going to be contains, not you, not you. What the hell is happening? Control C. And yeah, pretty really simple functions. So much memory being created, but okay, it's working. Now let's complicate it a little bit more. What was it? So, and you point to those, and then you point to N3 and N4. N3 points to N4 and N5, and then N4 dot edges and N4 pointed to N5. So the reordering correct order here is this, D, C, B, A, N4, N5. Let's actually do the one there. Let's put the 4 there. C. Oh, you get stuck in a loop. Why? N2 goes to 2 and 3, 2 and 3. And 3 goes to 4 and 5, 5, 2, 3, 4. Alright. Where's the loop? Actually, where is the loop? Okay, there's the loop. No, please stop. Big loop. Node C, edge length C, which is N3. Wait, edge length 4? Huh. Why? Why is it over 4? Because we're never changing edges, we're only doing ordering. So literally just doing those of the edges. Oh wait, this should be a 3 there. Whoops. Testing error. Yep, great. And to be fair, yeah, I don't actually need this here, do I? Or sorry, must be sliced though. Yeah. Honestly, I use the pen because it's what comes up in the LSB. It's like super quickly. So okay. Tweet topological sort. It's really inefficient, like quite. But you know, it's all right for now because I think it's working. So it just doesn't handle cycles, but we don't expect it to, I think. And where was I? The only thing I wanted to do now is over here on the parsing code, which sounds like forever ago now, is to build up those edges like we have and do a topological sort on them, on the nodes. And yeah, but I think it's a good place to stop now. We've done our topological sort, then we need to implement it into a parser. Thank you for watching. If anyone's made it this far, I'll see you in the next one.